been supported by several premier funding agencies, including DST, DBT, Ministry of Education, DRDO, and Royal Academy of Engineering in the UK and Tata Steel. He also led the implementation of the first advanced control project in the mineral processing sector, which earned the Best Project Implementation Award from the Ministry of Mines and DST. He serves on the editorial boards of several reputed journals and conferences and has been a visiting professor in Washington University and in St. Louis and University of Washington Seattle. Notably, Dr. Mitra has been named among the world's top 2% scientists by Stanford University, led study for the past 3 consecutive years, received the Faculty Research Excellent Award at IIT Hyderabad. His work has also been recognized internationally, including mention in the EU Horizon 2020 Battery 2030 Plus roadmap. With extensive international collaboration and multiple Best Paper and Project Award received by his students from bodies such as IFSC and INA, Dr. Mitra continues to make significant contributions at the interface of AI and engineering. We are truly honored to have him with us today. Please join me in giving a warm welcome to Dr. Kishalay Mitra. Thank you so much, sir, for being with us.
Yeah, thanks so much, ma'am, for the nice introduction. Okay, so should I start then?
Yes, yes, please, sir.
Okay, let me share my presentation. Okay. So, okay, yeah. Is my presentation visible?
Yes, sir. Yes, sir, it is visible.
Okay. So can you see the full screen or?
It is not full screen, but we are able to see your screen, sir.
Generally it goes to full screen. Why it is not going? So any idea probably quickly how to go to full screen?
Sir, when we go for the slideshow, that will be then slide is not moving. I think we'll keep in this pattern only. Last speaker
okay,
is having the same problem. So if you make in the slideshow, then PPT is not moving, slide is not moving.
Wonderful. So probably it is not, it is disabled from your end only because I am not able to see those icons. So I was not able to take it to the full screen. Okay, fine. So then we'll continue in this mode, right?
Yeah, that is correct.
Okay. Okay. Thank you so much. Okay, so good afternoon to all of you present for this IST approved online faculty development program on application of AI in chemical engineering. And thanks so much for the opportunity to Thadumal Sahani Engineering College for giving us the opportunity to present whatever limited research experience we have in the interface of AI and chemical engineering. So I will make my presentation. Okay. So this is the brief outline which I'm going to follow during my presentation. So I kept it a little bit this thing in mind that probably variety kind of audience is sitting. I'll not assume that probably uh, many things are known to the audience. So with that background, I will proceed. So First, I'll try to motivate you that probably means why we are going for AI. Okay, that would be followed by little bit fundamentals of optimization. Optimization is a huge subject. Means even a full course is needed in a semester in a IT kind of setup to give a proper justice to a subject. So what I'll be doing that I'll be showing you that the entire machine learning uses optimization every now and then, and it is basically sitting at the heart of machine learning. So that way, we need to know the fundamentals of optimization. And so I'll be briefly covering on an overall basis what a classical optimization does compared to and compare its performance with evolutionary techniques. Okay, a little bit I'll cover on multi-objective optimization because all these things would be needed when I'll talk to the next topic, which is surrogate optimization. Okay, so that's what initially I'll building up these tools and I'll talk about them so that it should not come completely from uh, alien nature. So I'll build up the platform for yourself and then I will talk about that what is surrogate optimization and how machine learning can be of great use in the field of surrogate optimization, or how probably uh, computationally expensive uh, chemical engineering application can make a huge benefit out of machine learning. And then I plan to talk about three different applications. Okay, and so one would be how to deal with steady state kind of data, and the second one probably how to deal with time series kind of data. Okay, and then the last one probably how to deal with image kind of data. Okay, so with this brief outline, I'll start uh, going ahead. Okay, so hope slides are moving. Okay, so the conventional fields of various engineering, so for example, mechanical, chemical, civil, uh, these conventional engineering fields, they are going through humongous phase of transition in past few decades. Okay, so for example, there has been tremendous progress in theoretical science. There have been excellent state-of-the-art experimentation facilities, ever increasing automation of enterprises. To give some examples, some more examples are stringent regulatory constraints related to safe and sustainable development, continuous pressure towards increased production, or omnipresent connectivity with access to high computing and storage capabilities. So all these different kind of things have been happening around us over last 2 to 3 decades. Okay, and due to which this our kind of conventional fields they're going through a humongous phase of transition. Okay, so there might be a lot of diversity, but one very common thing as an outcome out of all these activities, which is nothing but generation, processing, and management of data of heterogeneous nature. Okay, so variety kind of data are coming into picture. So with contemporary engineers handling data like never before, like chemical engineers, mechanical engineers, or civil engineers, these streams of engineering are at important crossroads. On the other hand, if you see, the field of computer science has experienced a rapid growth in terms of development and application of novel algorithms for handling such voluminous data and converting them into meaningful outcomes that becomes useful for common man. So in the fields of science and technology, such data based modeling and analysis is termed as data science, which has become the fourth paradigm of scientific discovery. The other three being empirical, theoretical, and computational in nature. Okay, so this is what exactly happened in the recent past, due to which the stream of data science have become extremely popular, and out of which the machine learning, artificial intelligence, deep learning, and all those streams they have come out. Okay, so in subsequent presentation, sometime probably during my lecture, I will show that probably machine learning, the learning part of the machine learning is nothing but playing with optimization tools and optimization concepts. Okay, so for some time, till that time I show you that fact, I would request you to accept this fact, and with that thing in mind, what I'll do, I'll be covering little bit of fundamentals of optimization, because the simple reason become because that this optimization is going to be used profusely inside the machine learning. So before we go and talk about machine learning, I would tell the very basics of few optimization concepts which I would need to perform machine learning more efficiently. Okay, so I will start with a very motivating example for which I will show you or I would introduce you some of the terms which we'll be using in optimization. So suppose I take an example, and this example is so basic that it will take you back to your plus 2 days. Okay, so we used to do differential calculus, and one of the chapters in the calculus was application of calculus. Okay, so there this kind of problem we have already solved. So in that way, our introduction with the concept of optimization goes back to our plus 2 levels. So suppose I tell you a statement like, I want to minimize the cost of manufacturing a cylindrical vessel with fixed volume V. Can you provide me a suitable diameter and height? So in that way, basically what I am trying to say is, suppose you can see my screen. Okay, so this is the cylindrical schematic uh, on which I am hovering my mouse. So it has two dimensions, right? One is the diameter and another is the height, D and L respectively. Okay, so I can come up with several combinations of this D and L so that I will get different kind of designs of cylinders. But what is my primary aim? That I have to design a cylinder whose cost is going to be minimum. Okay, but then if I don't put any restriction, then I will tell you probably, can you design a cylinder for me which will be having minimum cost? So then your answer would be obvious. You will say, okay, D is equal to 0, L is equal to 0 is my answer, because you told me to minimize the cost, and that's what the answer. So that is what we want to put a restriction there. So we say, okay, give me a design of a cylinder. That means find out the values of D and L of a cylinder, uh, which will be having a minimum cost, but at the same time, it should be having a fixed volume V. Okay, so that puts a restriction. So suppose I'll tell you, can you design a cylinder which is of 100 cc? Okay, so that means anything, any combination of D and L which is giving you cylindrical volume of less than 100 cc is not acceptable. Okay, so in that way, so the statement given to us is extremely important. By following that, what can we do? We can see there are few things in this statement. One is cost of manufacturing. Okay, that has to be minimized. So if we want to minimize the cost of manufacturing, I first need to define what is cost. Okay, and then there was another restriction told that cylindrical vessel will be having a fixed volume V. Okay, so volume of the cylinder also I need to define. So that we can do very easily by defining a cost function here. So cost function is nothing but the coefficient of cost for manufacturing the surface, which is CS. So coefficient means unit cost per area. Okay, and then there is another. So when you take this unit cost per area, CS, which is the unit cost for manufacturing the surface area of the side of the cylinder, you multiply that with pi dl, which is the area of the cylindrical surface. That gives you the total cost involved in manufacturing the surface of the cylinder. Similarly, you have top and bottom leads. Okay, and together their area is pi by 2 d square. If you define another cost coefficient T, which is unit cost per unit area, okay, and then you multiply that with the area of top and bottom lead together gives you the total cost for manufacturing top and bottom lead. So if you now add these two costs, one was cost of manufacturing the surface, another is the cost of manufacturing the top and bottom lead, that gives you the total cost of manufacturing. Now you will see very interestingly, this cost function is a function of L&D. If you change L&D, your cost changes. And that is what you precisely wanted, because you are now going to play with various combinations of L&D and you want to find out which leads to minimum cost. For that, you need to define your cost function in such a way so that that changes with the change in L&D. So that is what precisely you have done. So the first thing is known as cost function. Okay. And the second is the volume restriction. So volume of a cylinder, you know, 5/4 d square L. So that you write. Okay. So now you wrote three things, that D and L are your design variables, which you have the freedom to change. But by doing that change, you are going to see the change happening at the cost function, which you want to minimize. And by doing or by trying several combinations of D and L, you want to see that this volume restriction equation should be satisfied all the time. So these three things in optimization are known as or termed as objective function, okay, constraint, and decision variable. So these three things are given three different names. Okay. So decision variables help you to make your decision. Okay. Now your constraint and objective function should be also function of your decision variables, because you're going to change your decision variable, which should change your constraint and objective function. So in this way, optimization formulation is done. You remember, for optimization, these are the three pillars: objective function, constraint, and decision variables, which should be present in a formulation. But sometimes, so objective function and decision variables should be present all the time, whereas constraint might be present in some cases, might not be present in some cases. Okay, now how to solve this problem? Now you see there are two variables, D and L, but there is an equation given to you also, the volume equation, which connects D and L. So since this is an equation, not inequality, using this, you can eliminate one of the variable. Either you can express D in terms of L, or you can express L in terms of D. Whatever way you do, you can eliminate one variable. Okay. And thereby your original objective function cost, okay, which was function of L and D, can be now converted into only function of one of them. So we substituted L using this equation, and the cost function became function of only D. Okay. Now this is like your any function fx given to you, you want to minimize that function. So what do? You take the first derivative of that function and you get that to 0. So that is what we have done here. Df dd we have calculated, and you get that to 0, which gives me DNL. So in this way, you quickly saw through this very simple motivating example how to formulate a problem and how to solve it also. Okay. Now, if the problem is smaller in nature, suppose 2-3 decision variables, one objective function, one constraint, you can solve them using such simple methods, okay, which is known as analytical method. But if the problem is very complex, very large in size, means number of decision variables are 10, okay, means though 10 is not very large, okay, million, billion decision variables is also possible. But then even for 5 to 6 variables, solving it in the simple manner would be very tedious. So those kind of problems are solved using numerical methods for handling optimization. So that will be discussing next. Okay. So but before going there, I would say that this example was very simple. What we could see here. Okay, we formulated the problem here, and then we solved it also. But then our journey doesn't end after solving it. We can do even further. That is what the whole beauty of optimization. So you found out the optimal value of D and optimal value of L. If you try to take their ratio, this L by D gives you CT by CS. This means what? This means this gives you an immense information. So basically, this says that your whole design problem finally boils down to L by D ratio equals to CT by CS. And CT by CS is nothing but your unit cost, which you assumed during your optimization formulation. So what you are saying that your unit cost for manufacturing top and bottom lead and unit cost of manufacturing the surface, this ratio is going to tell you what kind of L&D optimally you're going to get. So that's pretty informative, right? Because this particular information says why Pepsi can looks like a Pepsi can. Because in case of Pepsi can, there would be an opening closing mechanism at the top lead, right? So definitely CT would be higher than CS. So this L by D ratio goes more than 1. So that is what Pepsi can's length or height is more than its diameter. So what we are saying, optimization doesn't help us only to solve a problem, but also tells us probably what answer you are getting, why you are getting so. So it's extremely informative. It not only tells us probably how to solve a set of problem, but parallelly tells us probably why you are getting certain kind of answers. Okay. So with that motivation, what I would say that simpler optimization problem can be solved using this analytical method, which I showed you. Okay. But then moment the problem size becomes bigger, we go for solving them numerically. So let us take a very simple example of how to solve such numerical problem. Okay, so this is one of the very simple numerical algorithm which I uh, displayed in the slide, which is known as steepest descent algorithm. So actually, I would say optimization is an iterative process. When we do numerically, we find the solution not in one shot, okay, but by performing several iterations. So for example, you'll start with a point, okay, and from there you will move in a direction. Okay, so basically, I hope you know the meaning of such a such a thing, which is known as contour. Okay, so this is very simple. That suppose if you have a elliptical bowl, okay, and if you try to see it from the top, so its projection on the 2D plane, though it's a 3D figure, would look like this. And these are known as the contour lines. Okay. So any particular colored line, everywhere the function value is same. Okay. So that is what is a contour is. So similarly, if you have a means a sphere, if you cut it maybe from the middle of it along the diameter, okay, and then you try to project it from top, or even if you try to project the sphere from top, you are going to get these circular contour lines. Okay, similarly, elliptical bowl is going to give you this elliptical contour lines. So now, so in this case, the outermost line probably tells you that it is having everywhere on that line. Okay, your function value is say 10. The green thing, if you can see everywhere in that function line, its value is say 8. So in that way, as you go closer towards the center, your function value decreases. But everywhere on a line which is of a unique color, the function value is same. So I mean every point on this green line, the function value is same. Okay. So in this way, suppose you start from a point. From there, your target is to go to the point where function value is 0 because you're trying to minimize the value, right? Okay. So how can we make that journey? Okay. So generally, how a numerical optimization is performed, it starts from a point. From there, it starts moving in a direction. There are different various ways you can probably find a direction. Okay, so one of the ways of finding a direction is to move in the negative of the gradient direction. Because for a function at any point, the gradient direction shows you the direction of maximum increase of the function. So since the positive gradient shows that the maximum increase, if you take negative of the gradient, that shows you the direction in which the function value decreases the most. And you are trying to minimize a function. So that means you will choose a direction in which if you move, your function value decreases. So that's what, starting from a point, you move in a direction. You say along everywhere in the green line, the function value is suppose 8, as I told. Inside line, the function value might be 6. So if you move in this direction, your function value decreases. But it decreases up to a certain point. After that, the function value again increases. So that means you not only move in a direction, but you have to stop after some time. Okay, so moving in a direction can be done by finding a suitable direction, which I told you generally negative of the gradient is taken as a direction. And in that direction, how much to move is basically mentioned by step length. Okay, so most of the optimization techniques, they differ from one another in terms of either of these two. Okay, I means suppose method number 1 takes a direction in certain way. Method number 2 takes the direction of movement in some other way. Okay, or method number 1 takes a direction or takes probably one way of step length implementation, whereas the method number 2 takes another way of step length implementation. So in an algorithmic fashion, if you see this particular line, so it says you start with a point xi, and then you perform some modification on that xi, which is written by lambda isi. Okay, means you are moving in a direction of lambda I. In that direction, you are going to move lambda I scalar. Okay, in that way, you go to a new point. So you can just remember that you are starting from a point, from there you are going to another point, from the new point you go to another point. In this way, in this zigzag fashion, you find the minimum. Okay, so this is one way of finding it, where derivative information is used profusely, because you see, as a direction, I decided to move in the negative of the derivative direction. So here, for movement from one point to another, we decide to move along the direction of the derivative. So derivative information is used profusely in optimization method. So this kind of techniques, which uses the derivative based methods, broadly you can call them as classical algorithms. Okay, but there are certain drawbacks of derivative based techniques also. So that's what people thought, okay, why not to use some other technique which does not use derivative information. So another class of algorithms known as evolutionary algorithm, they came into picture, okay, which can overcome some of the drawbacks which we see in the classical algorithm. Okay, so very briefly, how probably such kind of evolutionary algorithm works. So basically, it starts with many candidate solutions. So what I told, in case of classical algorithm, you start with one solution and you keep on improving it. Okay, whereas in case of evolutionary algorithm, you start with many such solutions. Suppose this is the function whose minimum you're trying to find out, right? So instead of starting with one point, you start with all these black points. Okay, and then you improve it over several iterations, which in evolutionary term we call as generation. Okay, so you perform certain changes in these black points, and then over several iterations they become the these orange points. Okay, and then finally most of these points converts to the purple point, and you can see that you could find the minimum. So this particular function which has been used here, you see it has one local minima here, another local minima here, but then there is a another local minima here which is better than the other two. So under this several local minima present, one which is having the lowermost function value is known as global optima, whereas the other optimas are known as local optima. Okay, so now, so this set of evolutionary algorithms, they are inspired specifically by the biological process happens in human or animal evolution. Okay, so that's what they are known as evolutionary evolutionary algorithm. And one of the popular one in evolutionary algorithm space is genetic algorithm. So here I told you are going to start with all these black points. We call them as population of solutions. And we are going to see how good they are based on their objective values. I told you before starting this particular algorithm that there would be nowhere the derivative would be used. So we are not using the derivative information here. We are just using their function values. Means at this particular x, what is its y? So y is your function value. Function value is your fx. Okay. Now based on the function value, we will come to know which one is good and which one is bad. So if I tell you to compare this solution versus this solution, you know this solution has a lower function value and you're trying to minimize the uh, objective function. So this solution would be better than this. Okay. So depending or probably evaluating the function value for all candidate solution, we'll come to know which one is good, which one is bad, and we'll perform some selection process, and better solutions will be chosen over the inferior solution. So in the next iteration, okay, you will get probably better of the lot than with which you started your journey. So initially you will be having the population of points. So that's what you see. Initially you will have these black points, but since you're minimizing the function, orange points are much closer to the individual optimas. Okay, so orange points are better. So you start with a population, you check how good, bad they are by checking their fitness, and then you select some of them over a competition. Okay. Okay. So you can easily pick two of them and see which one is better. So in that way, you can pick the better ones. Now you got a better set of solutions, and then you are going to change those solutions. Okay, because in classical optimization also you have seen that you started with the solution and then you modify it. Okay, in case of, but then here the modification happens using derivative information, whereas in evolutionary algorithm it doesn't happen using derivative information. So we use certain parameters called crossover and mutation, which helps you to change the quality of the solution. So now I'll just give you an example in the next slide. You will understand that after selection, we are going to choose few selected solutions which are so far better than the rest of the lot. We call them as parents. Okay, now these parents go through operations like crossover and mutation to give birth to children. Okay, so new solutions basically come up, which we are going to call them as children. Now, those childrens, they again go through the fitness evaluation. Okay, again selection and crossover mutation. So this loop continues. So you can see that on the right side schematic. So you start and your population is initialized, then you compute their fitness. Okay, and then you perform a selection operation based on fitness, you choose certain good ones compared to the rest, and then with the chosen one, you perform crossover mutation to come up with new solution. Now this new solution again goes through following this loop. It goes for again fitness computation, selection, crossover mutation. This runs in a loop till a termination criteria is satisfied. Okay, so this is another way of performing optimization where we have not used the derivative information. Okay, so maybe one very simple example is basically means there were quite a lot of animation in my slide. I'm so sorry. Probably means I'm not able to run them in running mode. So probably those animations will be missed out. Okay, so we'll leave with that. So, okay, I think this slide was having quite a lot of animation, so that would be missed out. But anyway, I'll try my best to tell you probably how genetic algorithm works. So we are trying to maximize this function, okay, which is sin x, x goes from 0 to pi. Okay, so what we do in the beginning, we uh, So X is my decision variable. We codify this in terms of binary string. Okay. So one string 01001 that signifies 1x. Okay. So that X codification is performed by this binary string, and each of these binary string, their uh, decodification can give you, using just binary algorithm, this kind of decoded values. Okay, 9, 20, 1 and 26.26. So let me see whether I can figure out. Okay, so this is the way binary string is basically evaluated. So you have 01001 and you find a value out of it, okay, by doing this uh, binary operation. So you have 5 bits, right? So 2 to the power 0 is multiplied with the last position. 2 to the power 1 is multiplied with the last but one position. Okay. Similarly, you use this binary operation to decode this. So here you can easily see if your decoded or rather string value is all 5 zeros, then your decoded value would be 0. If all of them are 1, then your decoded value would be 31. That means if you take a string which is a 5-bit long length, it gives you discrete 32 values starting from 0 and up to 31. So your counting starts from 0. So that's what altogether 32 values. So what you do, your x is a decision variable which is continuous in nature. You represent that x in terms of this 5-bit long string. That means you are considering 32 equally spaced possible values in between 0 and pi. Okay. Now you try with one such population of strings. Now I already told you how to decodify each of these string. So 01001, if you decodify, you will get a decoded value of 9. Okay. So, and then you just use another formula uh, which helps you to find a real value out of this decoded value. You just see here how the decoded value is mapped between x min and x max. What is your x min? 0. What is your x max? Pi. Okay, because your x varies between 0 and pi, and you have to find its optimal value in between 0 and pi. So you use this formula. Okay, so now if your all 5 bits are 0, your decoded value will be 0. So that particular thing will be mapped to it. So your second term goes to 0. So your x becomes x min. Okay, if all your decoded values are 1, then its value will be 31. So your decoded value will be 31. 2 to the power 5 minus 1 will also be 31. So these two cancels out. Your x becomes x max. So in that way, whatever value you get in between through this different combination of 5-bit string, they would be mapped between x min and x max. Okay, so in that way, you can find these real x values, though initially you're presenting them in terms of binary bits, and then when you know x, you can find fx. Okay, so for each of these 4 solutions, you know the fx values. Now you want to see that, okay, how good or bad these solutions are. So then you first find out the average value of the population, which is nothing but f average. So you sum up all these f values, okay, and take an average of that, which is 0.569. Okay, now each solution you will take and you will find out how good or bad with respect to average. So 0.791, it is better than average 0.569. How can you find? You take the ratio of these two, and it would be, if it is more than 1, it is above average. If it is less than 1, it is below average. So in that way, you'll see there are 2 above average candidates, but then there is 2 below average candidates. So you need to perform a selection operation here. You perform that selection operation and you decided that, okay, the second guy gets 2 copies because that is the best. You see their function values and you are trying to maximize the function. So 1.58 is the maximum. So this candidate gets multiple copies to select it for the next generation. Whereas this is an inferior point which gets no copies to go over the next generation. Okay. So that way what you are saying first, so we call this each of the solutions as chromosomes. Okay. So there are 4 chromosomes here. Okay. So first chromosome will get 1 copy. Second chromosome gets 2 copies. Third chromosome 0 copy. Fourth chromosome 1 copy. Okay. So accordingly you just copy them here. Okay. Now up to which the selection operation is performed. Once you selected few of the good solutions, you go to new kind of candidate generation through these steps, which is nothing but crossover. So in crossover, what happens if you take any 2 chromosomes and then you take a randomly selected site, which is shown as this red vertical line. Okay. And then all the bit information on the right side of that vertical line is swapped. Okay. So at the top, uh, right side of the vertical line was 0, 1 and 0, 0. You see, for these 2 chromosomes, that 0, 0 which was present in the bottom one came above. Okay, and 0, 1 which was in the above came in the bottom. So in that way, string information exchange happened, and due to which your solution got changed. Now here the philosophy is, since you have taken selected parents, which are good because just before this step you did the selection operation. So since you have taken selected parents, they have better properties. And when you exchange information between the parents, you are going to get children which are also good in property. But we need to basically prove that okay, you are getting children which are better than the population you started with. How do you do that? For individual all these chromosomes, you again find the decision variables, their x values and their fx values. After find out fx, you take f average. You see, this f average is better than the previous population average. So that means you are improving. Okay. So in that way, in this picture, you can see probably optimum is somewhere here. Initially, there were so many x points here and there, but finally, in the next generation, your orange points are coming closer to the global optima. Okay, or probably the optima. So in that way, your uh, algorithm is converging. Algorithm is trying to give you better solution. Okay, so in this way, this is another class of algorithm, how probably which shows you how GA works. So I don't know whether I'll be able to. Okay, I think I can run this video for you. That's a very good luck for me. Okay, so this is a Himmel value function, 2 variable. You see there are 4 optimas here. And how GA works, you will see initially we are standing at generation number 1, where so many solutions are spread well across the x1 and x2 variable space. You see those black points are everywhere. Now if you run that video, you will see how new points would be emerging. Okay, inferior points will be rejected, better points will be, superior point will be encouraged, and then you will see the entire population which is spread everywhere finally go and converge to one of the optimas. Okay, there would be this kind of uh, scary points or rare points uh, once in a while that happens due to mutation. Okay, but then if they're good points, they will be retained. If they're bad point, they would be rejected. By means of what? By means of selection operation. So in this way, you can see that initially you created so many candidate solution across the entire search space, and then which followed the genetic algorithm or the logic which presented through this example, and then the whole entire population goes and converges to one of the minimums. So this is also another way of performing optimization without taking help of derivatives. Okay, so I will quickly tell you probably certain differences between these classes, these 2 classes of algorithm, because they are extremely, uh, I would say, extremely popular 2 classes of algorithm. classical algorithms are there in practice since 1900 time. Okay, whereas this evolutionary class of algorithms are relatively recent, and but then they have certain capabilities which the classical algorithms do not have. Okay, and so that's what they became extremely popular. Okay, so some of these probably comparisons are mentioned here. I'll just read a few of them. That um, actually, first point, we could see GA works with coding of decision variables. So this coding of decision variable has a added advantage, because when you decode, actually you generate integers, and then by mapping linearly, you convert them into uh, real variables. Okay, so if you have a problem where you have to use both real variable and integer variable, there GA kind of formulation can help you a lot. Okay, so that is one way you can say that evolutionary algorithms, especially the binary GA, can handle both discrete and continuous optimization problems together. Whereas the other classical method which I showed you initially on gradient descent, it can only handle continuous variables. Okay, uh, so the second point, that evolutionary algorithms can handle discontinuous function. Okay, because the function needed to be continuous is a requirement for an optimization algorithm where derivative is needed. Whereas genetic algorithm kind of optimization methods, they don't use derivative information. So that's what it really doesn't matter whether your objective function is a continuous function or not. It can handle discontinuous function also. So these evolutionary algorithms are, for that sake, genetic algorithm specifically work with population of solutions. Okay, so that increases the chances of finding the global solution more. Okay, so suppose you're talking about a function, okay, where the life is pretty complicated. Okay, so if you talk about this function, you see there is only one minima. Okay, okay, or probably this might not be the right example. You take just this example. So this is a circular contour, this is an elliptical contour where the number of minima is only one. Whereas if you talk about this particular example, or probably this particular example where you have several minimas. So if now, or in this case, you see this minima, this minima, this minima, three minimas are present in this function, out of which this one is the global minima, whereas these two are local. So how can I find the global minima in presence of local? Because the way classical algorithm works, it starts from a point. First of all, it works with a single point. It doesn't work with population of points. It starts with a point and keep on improving the function. And one of the criteria used in classical method is you stop when you find the derivative is zero. So if you start from here, you will come here and stop here. You don't have any mechanism to overcome this optima and then go to the next basin and see whether the optima present in the next basin is better than your current basin. So it doesn't have that mechanism in place. So that way, classical algorithms can be only working for or finding local optima. Whereas these evolutionary algorithms, they can find the global optima in presence of several local optima. So in that way, you can see there are many such advantages for this evolutionary algorithm, which made them quite popular in the recent past. Okay, so this is up to the optimization of single objective. And then probably I'll very quickly cover the case of multi-objective optimization. Okay, and I'll just give you the notion that what we are trying to do in multi-objective optimization, and from there we'll quickly go to machine learning. Okay, so suppose we take an example of car purchase. Okay, so when you go for purchasing a car, there are several parameters which you can see before purchasing a car. So suppose we identify two maybe the most important parameters. One is cost and one is comfort. So my choice of two parameters may not match with the choice of anyone else's. Okay, so that's a totally different thing. Means, but for an example, if I see that suppose two most important parameters for my car purchase is cost versus comfort. Now, if you see a typical scenario in the market, there are low cost car which gives us low comfort. Okay, so for example, Nano kind of car or Maruti 800 kind of car, where cost is very less, but then comfort is also very minimal compared to the alternative other cars in the market. So on the other end, you'll see Mercedes-Benz or many kind of luxury cars where the cost is extremely high, but at the same time you are going to get a lot of comfort. Now, if I ask you that which one is the better choice or which one is the best, so probably many people start jumping and think and then probably come up with one solution. You'll see probably everybody is giving you different answers because for this problem it's very difficult to find only one answer which comes out to be the best. Okay, the best evidence is had uh, Maruti 800 been the best car, then probably other cars would have not been there in the market. And similarly, if bench were the best car, then probably no other car would have been existing in the market. Okay, so that way, for such kind of optimization problem where multiple objectives are involved and they are conflicting in nature, okay, then there might not be a single answer. There might be many answer for that optimization problem. Okay, so for example, let us see what are the nature of cost and comfort. Okay, so nature wise we have seen increasing cost gives you more comfort. Okay, decreasing cost gives you less comfort. But what your objective is? My objective is to minimize cost, but maximize comfort. Okay, so you see the trade-off because here cost and comfort goes proportionately. Increasing cost gives you more comfort, decreasing cost gives you less comfort, but you want to minimize cost and maximize comfort. So there is a trade-off. So if you have multiple number of objectives and there is a trade-off involved among these objectives, then you're not going to get a single solution. You're going to get a set of solution, which is known as Pareto optimal solution. So then best example is our market. It's not like our theory. The best example is our market because there are plenty of cars available in the market where uh, based on our requirement, probably one car suits our requirement. Some other car suits someone else's requirement. Okay. Otherwise, there would have been only one car in the market instead of so many being present there. So this is what the overall notion of multi-objective optimization problem. For the time sake, you just remember that, okay, in case of multi-objective optimization problem, why multi-objective? More than one. Okay, but then is it like only more than one number of objective function is there in a problem qualifies that as a multi-objective optimization problem? The answer is no, because when you have more number of objectives involved in a multi-objective optimization problem, as I told you, there has to be some trade-off among these objectives. Okay, so and how that trade-off fits into this problem, that also I have shown. Okay, so maybe for the time sake, I'm not covering quite a lot of it, but then I'll quickly tell that since we talked about this genetic algorithm, okay, so one very popular multi-objective optimization algorithm is non-dominated sorting uh, genetic algorithm 2. Okay, so very proud moment for us. This is extremely popular algorithm, and this is fortunately developed in IIT Kanpur lab. Okay, and I was quite fortunate to work with the inventor for the NSGA 1 version. Okay, when I was doing my master's in IIT Kanpur, and then little 4 5 years later, NSGA 2 came around 2002, and then after that, it made a huge journey, which made all of us very proud about the fact that this is one of the most used algorithm for solving multi-objective optimization problem. So if you see what is there in this flow sheet, so this flow sheet matches with quite similar. The flow sheet I have shown in case of single objective genetic algorithm. Only thing, there is one block here which is known as non-dominated sorting. Okay, which is performed here. Okay, and rest of the things are quite pretty same. So I'm not going into non-dominated sorting or not. Neither I'm going for describing the NSGA2 altogether. Here I'll just try to see. Okay, again I'm fortunate. I'll be able to run this thing. So you just see probably what happens. You are starting with a population, okay, and then this is your Pareto front. You see the solid line, and you see how solutions are gradually migrated over the Pareto solutions. First, it is finding out it, and then it is spreading its tentacles over the entire domain. So this is the strength of the algorithm, how it works. So this is the final solution, but you saw how it was achieved. It was started somewhere from here, where initial population was there, and from there it gradually migrated, came to the actual function at some point in time, and then from there it improved the solution even further. So you can see it probably. So these are the trade-off lines along which the solutions are there. Okay, so these are different test functions on which this NSGA2 algorithm is used, and shown that how it can efficiently find out the trade-off solutions. Okay, so these are the three building blocks I was planning to talk about. First, about the optimization fundamentals, because this optimization is sitting very much in the heart of the machine learning. The entire learning part of machine learning is nothing but optimization. So that's what the optimization is needed. And then we talked about three techniques: how to solve it analytically, and then how to solve it numerically, first through classical methods and then through evolutionary methods. And then we didn't confine only to the single objective optimization. We also discussed about multi-objective optimization. So with this brief background, we can probably now slowly move towards uh, applications of machine learning in chemical engineering. And the one of the topic which I chose for today's workshop was surrogate optimization. Okay, so now let us see probably what is surrogate optimization. Okay, so so you can see this optimizer box, right? So what it does, it sends the decision variables to a function. For a chemical engineering process, you can build a process model which is going to act as your function. Okay, so to that chemical engineering process model, you send the choice of decision variables as an input, and you run or simulate that particular process model, and you return objective function and constraint values. So optimizer takes that, and then it changes the new decision variables in such a fashion so that your next iteration objective function and constraint value comes better than the previous one. So in this way, the improvement happens, right? So it's an iterative process, which you probably roughly understood by now. Okay, so now where is the trouble? Or probably what is surrogate assisted optimization? So we are talking about this physics-based model, right? So suppose there is a chemical uh, process, say for example, crystallization process. So you generally model that crystallization process to keep track of the crystal sizes. You use population balance models. Okay, so population balance models helps you to keep track of group of particles. Okay, so you keep a track of that, and how probably a particular group grows in size, how a particular group uh, goes through the breakups. Okay, so in that way, so suppose the entire size fraction is divided into 4 groups, and then you try to track probably how different particle sizes, different particles of different sizes move from one particular group to another particular group. Okay, so in that way, the population balance model happens. So for writing those physics-based model, you try to capture smaller to smallest kind of phenomena, and you write a physics-based equation for them. So when you do this kind of detailed modeling, the whole physics-based model becomes extremely computationally expensive. So you are going to keep track of smaller phenomena. You are going to consider them in your model. So that model becomes computationally very expensive because you will write the PDE equation. Within that PDE, you will write equation for every small thing happening. And finally, it will be a jumbo model. Okay. Where probably if you say consider means uh, finite element methods, okay, finite volume methods. If you use those methods to solve your equations, so for example, computational fluid dynamics CFD models, okay, where you solve Navier-Stokes equations, which are nothing but the PDEs, partial differential equation, and you use uh, finite volume methods to solve them. Okay, finite difference method to solve them. So each one of them is going to take a lot of time. So one solution might run for 7 days. That's what happens in many of our defense projects. Okay, so because there we look for very precise information. So you might need to go for a very small grid size, and solving that even in parallel computation framework takes a lot of time. That we are talking about only one function evaluation. Okay, so one function evaluation suppose takes 7 days, and then if you want to solve this optimization problem in a genetic algorithm setup, then one generation is having say 100 population and you want to run it for 100 generations. That means you need 10,000 function evaluations. One evaluation takes 7 days. 70,000 function evaluation. Okay. 70,000 days. Okay. So if you even use such a technique and give a solution, your client is going to tell, okay, probably I'm not going to get the solution in my lifetime. Okay. So that becomes a tremendously computationally expensive or computationally prohibitive exercise. So how to run it faster or how to find a solution out of this problem? Okay, so that is what is surrogate assisted optimization. So what we have seen that, okay, this physics-based model, evaluation of this physics-based model is computationally expensive. So what can we do? We cannot integrate that with the optimizer, because optimizer is an iterative process which calls this model for so many times, and it takes a lot of time to finish this optimization. Okay, so that is troublesome. So what can be done? So the idea is, okay, I know I have a physics-based model which is highly accurate. So I collect limited amount of data using those physics-based model and build my input-output data set. And then can I use machine learning model to build a surrogate using that input-output? So once that is done, if I do the optimizer schematic I am showing on the right hand side, that would be extremely faster. But the trouble is how to build this ANN-based surrogate for this physics-based model. So here the challenge lies there. How can I build a very accurate data-based surrogate to the physics-based model? Because I know this ML, out of which suppose I say ANN, which is artificial neural network. So that is one of the ML techniques. You could have used some other ML technique also. So that ML technique based surrogate, once built, it would be very fast. It runs in a second. Okay, or millisecond, microsecond. Okay, if I attach that with the optimizer, that optimization run will happen very fast. So this is a very nice idea. Can I replace this computationally expensive, highly accurate physics-based model with a time cheap ML surrogate? But okay, I probably took care of the time. What about its accuracy? So that means when I substitute this physics-based model, I need to come up with such an ML substitute which is accurate also. Okay, so there lies a huge challenge. Okay, but then once this can be done, they can be used for uh, genetic algorithm kind of setup. So by now you know that genetic algorithm kind of setup gives you global optima, which probably your classical algorithm cannot give. But then genetic algorithm kind of setup is also computationally expensive because it doesn't work with single solution. It works with population of solutions. Okay, but it has positive point. It can give me global minimum. So I can use it, but then I need to build a very time cheap surrogate model for this expensive physics-based model. So that is what is overall surrogate optimization. Okay, so we'll go over there. We'll probably take an example. With the help of that, probably telling you would be much easier. So the first example is surrogate optimization using a computationally expensive polymerization model for process optimization application. So this is a chemical engineering example. Most of you, I believe, are chemical engineers, so you'll appreciate this example. So basically, this is the polymerization process. Okay, there are a lot of things happening. I'm not going into details of it, but then you can build a mathematical model out of it. Okay, so this particular mathematical model, which takes monomer concentration, initiator concentration, and temperature as input, and it solves a large number of differential equations, particularly ODEs in this case. Okay, and can predict you these four outputs: molecular weight, branching index, because this is branched polymerization, polydispersity index, and polymerization time. Okay, so for this system, there is 3 inputs, okay, and there are 4 outputs. Okay, so now there might be many outputs other than these 4. I'm not categorizing them, or we will more concentrate on these 4 outputs. Now let us see. Out of these 4 outputs, if you minimize polymerization time, then it will increase productivity. So your interest would be to minimize polymerization. But at the same time, in less amount of polymerization time, there would be not much of molecular weight or branching index or polydispersity index. But then if you see, these are the quality of polymer material which you want to maximize. So that means you have already seen the trade-off here. Less time gives you lesser molecular weight, branching index, and polydispersity index. But you want to minimize the time because that means maximum productivity, and you want to minimize all this from quality point of view. So you can originally would be interested in solving a multi-objective optimization problem. Okay, so multi-objective optimization problem is this bunch of 3 things you want to maximize, polymerization time you want to minimize, and your decision variables are this. There might be several other constraints. So this is the overall optimization problem you want to solve. Okay, I'm not talking about surrogate now. Okay, so this is the optimization problem you want to solve. The right time I'll talk about surrogate. Okay, now let us see how did we do it very quickly. So first we'll assume there is some uh, steps of mechanism, polymerization mechanism happening inside the polymerization reactor, and their corresponding reactions are there. So if we honor this, we can write the rate expressions. So each of the monomer, dimer, trimer, tetramer, oligomers, okay, you can probably track. And for each one of them, you can write the rate expressions. So that leads to tens of thousands of ordinary differential equations with their initial value mentioned. So they are set up ODE IVPs, ordinary differential equation initial value problem. So one such equations of that sort is shown to you in this slide. Now you do all these things, okay? So that gives you large number of ordinary differential equations, initial value problems, okay? Then you used moment-based approach, which helped you to reduce these tens of thousands of ODEs into some relatively manageable number of ODEs, which in this case is 285. Okay, but and using those ODEs, you can probably predict their properties, which has been shown here. Okay, but you can see here that you see some of those properties are taking sudden increase, which nature shows that your differential equations are stiff in nature. Means in a relatively smaller time, it shoots up. The value shoots up. So that's what you could write the moment balance equations and reduce your tens of thousands equations to 285 stiff non-linear ODEs. Okay, so okay, we know there are established gears method to solve such kind of complicated equations. So you solved it, but then once you solve your model equations, you need to validate that with some experimental data. Otherwise, nobody is going to believe what you model is correct. Okay, because you modeled using certain equation. If they give predictions which is not really matching with experimental data, who is going to believe us? Nobody. Okay, so that we did. Here you can see the symbols are basically the experimental data, whereas the solid lines are predictions. You can see they are nicely matching. Okay, so once such kind of model is ready, you can solve this multi-objective optimization problem given here. Okay, so you solved it, you got the Pareto solutions. Okay, and everything is done. I'm not going into further explanation of this problem because our aim is to tell you what is surrogate optimization. But then while doing this, we realize probably this optimization exercise takes half a month. Okay, so and that was really not acceptable to a client. Their interest was probably how can we make it faster? So can you give me the solution in 2 days, 3 days at max? I know you're solving a set of complicated equations, but then half a month is too much. Okay, so to address that problem, we took help of surrogate optimization. Okay, so surrogate optimization is what I told you earlier. So I'll quickly go back there. So there will be an optimizer here. So you can assume that is an SGA2, and this is your polymerization model. Okay, now this polymerization model, when amalgamated with this NSGA2, that takes half a month to solve the problem. And you want to make that problem solution faster. So your aim is, can I replace this highly accurate physics-based model with the help of an ANN-based artificial neural network-based machine learning surrogate. Okay, so that's what the whole aim is. Okay, so before going there, now let us quickly go then probably very briefly how ANN works, because this is an ML in chemical engineering workshop going on. I believe definitely earlier eminent speakers, they have covered quite a lot of ML, but still I'll cover it in a very short fashion. So what you have seen, you have 3 input and 4 outputs, right? So you see, you have 3 inputs, okay, and 4 outputs. So this is a MIMO model, multiple input, multiple output model. Okay. So you can use this model and generate minimum amount of data and then make use of that data to build the machine learning model. Okay. So what we are going to do, okay, since we have already seen this case is pretty complicated, a lot of non-linearity, a lot of sharp features are there when the state variable changes with time. Okay, so we thought, okay, instead of building one model which takes care of all 4 outputs, can I build 4 models taking care of 1 output? Means my model number 1 will connect all 3 inputs with the first output. My model number 2 connects all 3 inputs with the second output. Similarly, third model and fourth model. Okay, so we are talking about a neural network which is having 3 inputs and only 1 output. And such 4 models we are going to build. Okay, now how a neural network works. So since I talked about there are 3 inputs, so I will form an input layer where all these 3 inputs would be there. Okay, in polymerization example, they are monomer concentration, initiator concentration, and temperature. Okay, so MIT. Now that has to be connected with some objective, which is suppose molecular weight. Okay, so how this is done? Okay, so this is known as input layer, and the one which is in the last is known as output layer. In this case, it is predicting the value of molecular weight, so that becomes my output layer. Okay, in between what happens? Okay, we take each of these input, multiply that with the weight, okay, and then bring into this block. So if you see, this particular block is connected with all the inputs. So every input is multiplied with a weight and brought it here, and then we sum all three of them. So this is the summation block. Once that summation happens, with that the bias is added, and that summation of product of every input with weight along with the bias is going to give you this y, and that y passes through a nonlinear activation functions to give you x. Okay, so that happens at every node. Okay, so in this particular architecture, what we have seen, input layer, that would be followed by another hidden layer where we have considered two nodes, and then that would be giving us output. This is the structure we have assumed. The structure could have been anything. There could be many number of hidden layers, and in each of the hidden layer, there might be many number of nodes. But finally, your input and output layer will be remaining the same. But in between, many things happen. So those number of hidden layers, how many nodes to be considered in each of the hidden layer, okay, and what is the nonlinear function to be used in means this activation function block. It can be log sigmoidal, it can be tan sigmoidal, it can be ReLU, it can be many other things. Okay, so they are known as hyperparameters of this neural network. But then you roughly understood how probably the forward propagation of information happens. I'll repeat. Okay, so there are three inputs. You assume certain values of weights and biases, and then you do all the multiplication, addition, what I told you to do. You multiply each input with weight, plot it there, sum all of them up, add bias with it, and then that whatever value is coming, because you have already assumed some values of weight and biases. Okay, remember you are assuming. Okay, and then you are getting y passes through the activation function, and then again certain weights, all these weights bias values are known, are assumed, and finally it will predict some value of molecular weight, which is y hat, means predicted value of molecular weight. Now for a particular input, you have already a ground truth value of molecular weight coming from data. Now, in the beginning, when you do not know the actual values of weights and biases, there is a very rare chance your predicted y hat would go close as y. There might be a significant difference between them. Okay, but if you choose your weights and biases values correctly, you can probably predict a value y which goes as close as possible to the ground truth value. And that is what is nothing but learning in machine. Okay, so and which is nothing but the optimization. So now I talked about three things in optimization: objective function, constraint, and decision variable. What are your decision variables here? Weights and biases, because you don't know them. You want to optimize. You want to optimize them. You want to find the optimum values and weights and biases, which gives you minimum error here. And how error is defined? Error is defined in this manner, which is known as MSE, mean square error. So your error is y minus y hat. Okay, you square it, sum with all the points, and then take a mean of it. You divide with the number of points, capital M. So that's what this is known as mean square error. So your mean square error is going to be different when you choose your weights and biases differently. You are going to start with certain values of weights and biases, and then finally you are going to give the optimum value of weights and biases, which gives you the minimum value of loss. So this is an optimization problem, which is nothing but the learning part of machine learning. So, so probably it might be a little late. I took that much time to convince you why I said in the beginning that the learning part of machine learning is nothing but optimization. And that's what we needed to spend some time for optimization. So I hope this part is understood. Okay. Now, how to choose these hyperparameters? Means what kind of architecture to be taken? Means you have, of course, 3 inputs. This layer is fixed. You have 1 output. This layer is fixed. In between, there can be anything. How many hidden layers? How many number of nodes in each of these layers? They can be different from one another. What is the activation function to be used? They're all decided a priori based on heuristics. The reason is very simple. Suppose I have been doing it for the last 10 years. I am in a position to give you a nice neural network model. You might be starting it afresh now. You are not in a position to give a good model. But why to create such discrimination? So that haunted us. So what we found as an issue in ANN, that its design is pretty heuristic based. I think probably 3 layer is going to give me, so I chosen 3 layer, but that's not the right approach, right? Okay. And then how many data to be used? These neural networks are extremely data greedy, but each data comes from simulation, which is expensive. I have a restriction in surrogate optimization that I can only use a limited number of them. Then what activation function to be used? Okay. And probably even if you give me 100 samples in a 3-dimensional room where you are sitting, how I'm going to place them in this room? Of course, if I want to characterize the function involved in this room, I'll place them most uniformly, right? Instead of placing all of them in one corner, then I can only characterize what is happening in that corner in pretty details, but I'll be blind. Probably what's happening in other part of the room. So what would be the sampling plan? Because each sample is costly. So I have to judiciously sample it. Okay. So all these things were not really done simultaneously. I'm talking about the time of 2016 when we did this. Okay. So around 2019, CMU, Microsoft, they started some activity called neural architectural search. Okay, so gradually this hyperparameter optimization became important, but we came up with an algorithm which we call as transform. Okay, which is which finds the trade-off between various. So basically, there are 3 objectives. We want to build a machine learning model, right? We want the model error to be minimized. Okay, but model error would be minimized if we use more number of samples, because these algorithms are data greedy, and more number of parameters, because more number of parameters will give you leg room to fit everything. Okay, so what is our objective? Our objective is opposite. We will try to build an ML model where we'll use less number of parameters, less number of sample points, but we'll try to minimize the error or maximize the accuracy. Okay, so again, if you see, this is an architecture determination optimization problem, because our decision variable would be all these hyperparameters. How many layers to be used, how many nodes would be there in the layers, what are the activation functions to be used out of a plethora of choices of them. So we are going to vary all those things. Every time we vary, you imagine your architecture is changing. And finally, not only you will get an ML model, which is highly accurate, you will get the optimal ML model in terms of its structure. So that is what transform does. Okay. And so quickly taking you back to the surrogate optimization example, okay, which we were talking about. So we had 4 objectives, right? One was polymerization time, another was molecular weight, branching index, and then polymerase index. For each one of them, you see there was 3 input and 1 output. But in between, there might be 2 layers. In between, there might be 3 layers. In between, there might be 1 layer. And then this number indicates in that particular layer how many nodes are there. These are all optimally decided by the algorithm transform. Okay, and then they are saying probably what is the number of parameters. So you see, with less number of parameters, probably we could develop the ML model. So what happened? And then another strange, probably good thing, I would say, we did. We used Sobol sampling. So what it does, it starts with certain number of data points, I suppose 30, and then incrementally it increases. But when it samples the expensive function, it samples uniformly. Okay, so that's what I was talking about. You need to sample it uniformly, right? Because you want to capture its nonlinear behavior. Okay, so you sample it uniformly. And one good thing about Sobol sampling is that suppose you ask your Sobol algorithm to give you 50 samples, it gave you. And then you asked your algorithm to give 51 samples. So what it will do, it will keep all the 50 intact and then 1 additional point. So which is not done by Latin hypercube sampling. If you use LHS, Latin hypercube sampling, it's 50 samples and 51 samples. They're all different. But if they're all different, then I have to run fresh simulations, right? Simulations are expensive. I cannot afford that. So I don't want to run additional simulations. So that's what we use Sobol. So when I say that I needed 70 function calls for polymerization time or needed 80 function calls for PDI, in this 80, these 70s are already embedded. So that means here if I write 70, 50, 60, 80, altogether means I used 80 function evaluations. Okay, so that means only 80 function evaluation my model is built. And then I put another 200 samples for its testing. I didn't do any miser here. I could have done that testing probably with only 20 samples. But then when we built your model with so cheap number of evaluation, you need to spend some time to check how good or bad your model has become. So that's what even more than double of the number of points used were used for validating the model. So altogether in 280 function evaluations, my model is built. Now such a model, if I use with NSGA2, it runs in fraction of seconds. Okay, so it runs very fast. Of course, there was some time involved for building these guys. And now for building these guys, each of this model, it would be all judged by how many function evaluations I have used. So altogether, if I see that originally probably I took 2800 to 800 number of function evaluation, which now got reduced to 280, 10x improvement. Okay, so that's what we are trying to. So this is a very small video which shows you what transform does. So this is your, you remember we had 3 inputs, M, I, and T. Monomer concentration, initiator concentration, and temperature. Now this is my 3-dimensional hyperbox. in which I am going to sample. Each sample tells me one particular coordinate of M, I, and D, means one set of value. That goes to a model. That gives me four outputs, all my objectives, right? PDI, polymerization time, uh, branching index, molecular weight. Okay. So in that way, this video will show you, you see how the algorithm is judiciously placing the samples uniformly in this three-dimensional box. The last column says it's a prediction versus output. So if it is a 45-degree line, that tells probably you're building a model very accurately. Okay. You see, initially it was so bad. Over time, you're going to get a very stabilized 45-degree line, which says, okay, your training got completed. So in this way, with less number of simulations, we could build a surrogate, and then that surrogate would be used for optimization. So if you use, you see here, one is ANN based Pareto, another is the expensive model based Pareto. So you will hardly find any difference between these green and red points, and you can see probably you could solve this problem pretty efficiently. And this gave you 10x time faster than conventional optimization. Okay, so you could make your optimization 10 times faster. Okay, so several occasions we could publish this work. They are way back 2016. Okay, and then I'll show you another example to probably excite you as the same time, and same time probably to provide you enough encouragement. Why should people go for ML? So ML has tremendous capability of capturing nonlinearity, which must be visible from here. This is something known as ACLE function. Okay, so this is the ACLE function, and this is the ACLE function which our transform built using ANN, using surrogate optimization. You see, hardly there is any difference between these two. We know where is the difference. Maybe the peak where the sharp minima is there in the actual function, there probably this built-in ANN took a little hit, but otherwise, and then probably that hit is compromisable for most of the engineering problem solving. Okay, but then it has tremendous capability to capture such kind of nonlinearity, because this is an extremely nonlinear function. These are actually, they probably do not happen quite often in real life problem solving. These are artificially created function to provide challenge to an optimization algorithm. So this is one such kind of function known as ACLE function, which you can see how nonlinear it is, like nonlinear at every layer. But then that kind of nonlinearity also your NN can capture. Right side, your NN captured ACLE, whereas on the left side, the actual ACLE. Okay, so this was the steady state data-wise optimization. Now, maybe little time I'll spend on how to handle dynamic data. So this is nonlinear system identification from dynamic process data for control applications. Okay, so this is a grinding circuit. Okay, so to tell you briefly, uh, this is the line by which the ore feed comes. Water is mixed, taken to the rod mill. The material is grounded, taken to a primary sump. From there, it was taken to a hydrocyclone. Underflow goes to the ball mill because those are relatively larger particle that goes through further combination. Okay, overflow goes to the secondary sump. From there, it again goes to the secondary classification hydrocyclone. Underflow goes to the ball mill. Overflow goes as product. So you have three handles: one ore feed, two water flow rates to change as an input. Okay, by which you are going to influence these six properties. Throughput of the serve. There are several size fractions: core size, mid size, and fine size. persistent solids, and recirculation load. Okay, so this is the overall operation. So we built population balance based, I would say semi-empirical model. Okay, because in hydrocyclone, ball mill, rod mill, there are several correlations which people use when you make a model out of it. Okay, so such a model is there. Our whole effort was to see, okay, this is a time series model. Dynamically, how each of the state of these process changes can be tracked by solving the differential equations in population balance equation setup. So we use that, we solved that. But then our aim was to see, can ML model such a dynamic process? Because the earlier one we talked about, which was steady state in nature. So next adventure was to see, can a ML model capture such a dynamics in a process? So for that, what we did, we generated 2000 data set. 70% of that is used for training, 30% is used for validation. So when we generate the data set, we basically used PRBS signals, okay? And then we used RGS signal to generate certain test data. Now on on so this is what the PRBS signals, okay? So these are the signals by which training happened. So you can see how is the ML model prediction. In this case, we have used LSTM, long short-term memory network. Okay. So this is one class of recurrent neural network ML models. Okay. There are several of them. Gated recurrent unit, GRUs, LSTMs, and RNNs. So there are processes by which the model can be chosen. It's not, we should not use systems blindly, but so there are ways to do it. I'm not going over there, but then in this case, what we did, we created training samples. Training samples were created by PRBS signals. Okay, pseudo random binary signals. Okay, you see the signals were basically uh, the original data. And you see, when I use that to train an LSTM model, the red lines are LSTM predictions. So they are quite nicely matching. So with training, of course, data will match. Otherwise, what training is happening? The actual testing was that when you show a new time series to your model, which it has never experienced during the training process, which is precisely your testing data, how is the prediction match? So that is shown in this RGS, random Gaussian signal. So these were all generated as testing data, and on which whatever ML model you have developed using this PRBS, that was used. And you see, this was an unseen data where the signals were going to come from random Gaussian signal, and that also predicted so well. So what LSTM architecture has to be used, and all those decisions were made by transform. And transform I have already described earlier, and you can see that if you used transform, then original data and LSTM, how closely they match, okay, it has been shown in this particular plot. So it was able to match the prediction very closely because we got very accurate results. Okay, so R2 validation data set came as 0.99, which was superbly accurate. Okay, and many cases such kind of R2 is not very easy to get. But if you perform transform kind of operation, means you are not only fixing your network and try to minimize the error. you change your network also. Thereby, you optimize your network performance also. Okay, so that's what the beauty of whole transform. So similar work, they were all published in reputed journals. Okay, and we could show that ML can capture the time series data as well. Maybe the last example, very quickly I'll cover, which is how to learn from images. Okay, so in very short, what I should say that the problem given to us is there is a green field. Now, can you place wind turbines in optimal fashion so that you can extract maximum energy out of it? Okay, so that is the overall problem. Now, power calculation of wind farm or wind turbine is done in this way. Though the first thing is the frequency factor of wind coming, the probability of wind coming from ith direction with jth speed. Okay, and then that is multiplied with the power. Now, power is going to come from turbine manufacturers. That is the power curve. So you cannot do much with that. Once you have decided which turbine you are going to place there, so the second term is not really going to help you at all, because that's a fixed thing. But you can probably play with this. Play with this means what? Now, what is this? This is like probability of wind coming from ith direction with jth speed. So there are two parameters, speed and direction. So we try to see that probably under what wind speed, what uh, which are most prevalent for wind farms. So generally it varies from suppose 3 to 18, which is really effective for a turbine. Okay, very high speed is going to spoil your turbine. Okay, stress problem or probably for its life. Very less speed is not going to give you any energy generation out of it. So suppose you identify 3 to 18 as the this thing, your range, and you divide it into 16 parts. So 3 to 4, 1. So in that way, your this speed axis is going to give you 16 values. Okay, whereas the direction goes from 0 to 360. You take bin size as 30, 0 to 30, one bin, 30 to 60, another bin. So in that way, there are 12 bins this side. Now you got a grade that 12 values of direction, 16 values of wind speed. And you are going to see probably out of 100 times, how many times a particular speed and particular direction appears. Okay, that probability you plot in the z-axis, whereas your x and y are your speed and direction. So in that way, you can easily draw this wind frequency map, which is nothing but your Fij. Now the question is, this wind frequency map varies with time. Okay, so how can we accurately design this wind frequency map? It's very difficult to model an image using mathematical equations, where AI can be of great help. So we used, I would say, the convolutional autoencoder, where my wind image is input, wind image is output. The same image is output. So the first image has been taken. Okay, you can take its heat map, two-dimensional pixel values, and it goes through several convolutional layers, and important features are extracted out of it, and then it is super squeezed in something called latent vector, and the same thing what has been done from left to right has been repeated for right to left. So this is the encoder part, this is the decoder part. Okay, now when you give an image, how the same image will come out of it? Only case when you tune your weights and biases nicely. So that is also one kind of ML training. But then this whole block is separable. So in this, considering this encoder decoder block together, you can give the same image and take the same image out to see whether the later part can generate this image. So in future, what you are going to do, you are going to separate them out. If the training is done properly, then you are going to say that my only decoder part I am going to use whose output is image, input is latent vector. That means what? If this is done by a machine, that means I will give you latent vector as an input and machine will give me as a result some image. That means it's started learning how to draw an image. So that helps us to capture the intricacy modeling part involved in WFM. And that is what exactly we have done. You can see these are the original image. When machine has learned, finally it could draw very similar accurately captured image like what it has seen while taking input. Okay, so in that way, we can use convolutional autoencoders to let a machine learn how to draw images. And here also we use transform to come up with optimal architecture of the CNNs involved. Okay, so these three applications, we used MLs quite extensively along with the transform kind of algorithm which has been designed by our lab. Okay, and we could show that not only steady state modeling but also time series modeling along with image modeling all can be successfully done using the judicious use of ML. Okay, so that basically ends up various applications I was talking about. Very quickly, I can tell you that this transform kind of algorithms, okay, we applied for several industrial applications. Polyvinyl acetate, long chain branching, which I have presented, sintering, continuous casting, induration, they're all still making industry applications. Grinding, I have already presented. Winstead modeling, I have presented. CFD based missile design. Okay, again, surrogate optimization was of great use here. And then optimal control of biochemical reactors. So there's one or the other different kind of very complicated chemical engineering applications on which we applied all these things. But these are not only the limited kind of applications which I am talking about. Our lab has been working on a lot of them connected with SDG goals. Okay, so let it be robust wind farm optimization and control, combustion of renewable blends. Okay, why to use only diesel for combustion? Why not to use green fuels along with it? And then what would be the optimal choice for that combustion? Okay, hydrogen production, bioenergy supply chain, battery management system, carbon capture process, maybe pollutant prediction, uh, or precipitation modeling, okay, prediction of rainfalls, crop classification, crop growth manufacturing, forest fire. These are the different applications on which you are working. And then there are so many of them as written here. I'm not reading it out for you. On the right hand side, this was basically the different kind of all possible AI uh, methodologies. We are making use of them and then trying to see how chemical engineering applications can be made better. First of all, we try to compare them with the existing methods to see which one is better. It's not like all the time machine learning is going to win, but if machine learning can give at par performance, then you are inventing another way of solving a problem. But in many cases, machine learning is giving you better performance. In that case, you are innovating a new way of analyzing the situation. Okay, so these are the different projects which are going on in our lab, funded by several funded agency. The only commonality in all of them that they're all based on AI/ML. People are really exploring, and you just see starting from ANRF, DBT, Tata Steel, uh, Ministry of Education, Royal Academy of Engineering. So we are working fortunately with all of them to see that whether ML can be applicable for problem solving with different scales, because there are microstructure related problems also. That's a different scale. The kind of polymerization I talked about, that's a different scale. Okay. And then image modeling of microstructures, that is also a different scale. So we were fortunate enough to come up with high impact publications out of this ML work. The whole purpose of showing this slide to encourage all of you that probably you guys join this ML wave at your individual capacity to solve different problems, and definitely you're going to get very high impact publications. Okay. And then probably most important out of any publication I want to highlight, probably this is the bottommost part. Okay. So this is the workforce, okay, who were continuously with the lab and whose work basically I presented. Okay. And the entire work of wind farm optimization we could collate in a recently published book. We are writing another book on water network optimization. Okay. And some of these things uh, means probably were mentioned during the introduction of the lecture. And last of all, thanks you so much for your immense patience.
Thank you so much, sir, for such
Yeah.
for such enlightening session. Participants, I would like to make request if you have any query or you any doubt, you can ask. Okay, so So, sir, on behalf of our organizing committee, I would like to express our sincere gratitude to Dr. Kishalay Mitra, so for such thought-provoking and enlightening talk on the application of artificial intelligence in chemical engineering. The session provided a comprehensive overview of how AI is reshaping modern process engineering, beginning with current trends in process engineering and the rapid growth and expanse of data science. The talk set a strong foundation for understanding why these tools are becoming indispensable in our field. The explanation of optimization fundamentals so that the participants can get along with the genetic algorithm example, and how these optimization problems can be helpful to understand the machine learning. We appreciate how beautifully Sir compared the classical and evolutionary algorithms. He also discussed about multi-objective optimization and energy 2 framework. Then we also discussed about uh, artificial neural network models, and we also discussed the case study about polymerization process using ANN models, how we can optimize the polymerization processes using ANN neural networks. Then again, he discussed about what are the challenges in ANN. He also encouraged us what are the opportunities, whether there are plenty of opportunities coming on the way with use of ML in chemical engineering field. Overall, this talk has broadened our perspective and inspired us to explore AI-driven solutions in our academic and research pursuits. We are really thankful, sir, for sharing your knowledge, experience, and valuable time with us.
Thank you so much, ma'am. It was wonderful talking to all of you. It was really very nice to see so many people joined and attending the talk. Hope probably this becomes helpful to all of you. We are in this AI, making AI possible in chemical engineering journey for last 10-15 years. We need a lot of people. So in this way, we can fantastically create the awareness among the people who are going to work with it in future. So thanks so much for attending or probably arranging, and then for such a nice workshop. And then thanks so much who all could attend. I just hope it was means helpful
Yeah,
and probably
definitely,
understandable.
definitely.
Yes.
Definitely, sir. Sir, you beautifully started with the basic example so that everyone can understand and get connect with it. And we also could see there are so many opportunities that we can work with sustainability goals, taking up our knowledge of chemical engineering and AI. It was really
Yes.
wonderful talk, sir.
Yes. Yes. Okay. Thank you so much, ma'am.
Thank you so
Probably,
much for giving
yes, if there
time
is
to
no more
all of us,
question.
sir.
Yes, yes. It would have been great had I been visited your institute. Probably that will happen sometime in
Yeah, sir.
future, because most of the cases when we give lectures in person, that becomes even more wonderful. But then collecting all the people is always a challenge. You did a great job by collecting all of them under the same umbrella. Thanks so much for this arrangement.
Sir, you are most welcome, sir. We will be delighted to welcome you in our institute, sir.
Thank you. Same here. Means whenever any one of you visiting Hyderabad, kindly visit IIT Hyderabad.
Definitely, sir.
Yeah.
Thank you, sir. Thank you so
Thank you.
much.
Okay. So
I
can I
thank,
leave now?
yes, sir.
Okay. Thank you.
Thank you, sir.
Yeah. Bye.
So, participants, there is one notice that there will not be evening session today during 6 to 8 slot. Participants, please make note there will be no evening session during 6 to 8 p.m. slot. So we will be meeting directly tomorrow during 11:30 slot. Again, I thank all the participants. Yes, sir. Yes, sir. Yes, sir.
हेलो
Yes, sir.
मैडम वीडियो स्टॉप करके एंड करना बाद में
Yes, sir. Yes, sir. Yes.
ओके ओके देन
Uh, so we will end the meeting here. So we will meet tomorrow during 11:30 session. I thank all the participants for being attentive and being the part of this FDP. I am ending the call now. Thank you, everyone.